Okay, today we're going to be talking about drawing free body diagrams. So before we can get started on any of this, we need to talk about Newton's first law. It states that an object in motion stays in motion in a straight line unless acted upon by an unbalanced force. So this means a push or pull will cause an object to speed up, slow down, or change direction. So none of those things can happen unless there's an unbalanced force. That's basically a summary of Newton's first law. So this is a flowchart basically proving Newton's first law. Okay, so we got two types of objects, objects at rest and objects at motion. So both of these have constant speed because an object at rest isn't moving, so its acceleration is 0. An object in motion has a constant speed. Now it is moving, so it doesn't have a velocity that's equal to 0. And so these objects will either stay at rest or stay in motion at the same speed and direction. And since the accelerations are 0, as we know about Newton's second law with that equation, so long story short, because there's no acceleration, there's no force acting on it, so these objects cannot speed up or change direction. Okay, so basically, objects just keep on doing whatever they're doing unless they are acted upon by an unbalanced force. So these are the forces we're going to be looking at. I'm going to describe these as we go over examples together in a little bit, but the main ones we're going to see are applied forces, gravitational force, normal force, friction force, air resistance force, tension force, and spring force. Spring force we won't see a whole lot. We'll see that a lot more when we talk about energy, but for now, those are the main ones. Now, most of these are going to be contact forces, which means they actually happen based on something actually pushing it, making contact with it. And there's also a second type called action at a distance forces. There's 3 of these, but the only one we're really going to talk about for now is the gravitational force. Okay, so this is a free body diagram. These are used to show the relative magnitude, which is size and direction of all the forces acting on an object. So these arrows here, those are the forces. The object itself is represented with a square, this box right here. Now, this one right here shows 4 arrows. 1, 2, 3, 4. Each of those is a force acting on it. Now, every single free body diagram isn't going to have all 4. Okay, some could have 3, 2, it just depends on how complicated the scenario is. Okay, so when you're looking at these one example at a time. So here, a book is at rest on a tabletop. Diagram the forces acting on the book. So throughout these example problems, you're going to hopefully understand what these forces represent. So with the first one, it's going to have a normal force and a gravitational force. So why do we have this normal force? Anytime an object is on a surface, like the book on the tabletop, we have that normal force. The normal force basically is what keeps the book from crashing through the table, because on the facing downward, we have the force of gravity. So basically, anytime we're on a surface, we have to have this normal force. Anytime we're on a planet, we have to have the gravity force. Second one, an egg is free falling from a nest in a tree. Neglect air resistance, draw a free body diagram. So in this case, we notice that we have an object in the air. So because the object is in the air, it's not on a surface. So what that means is there is no normal force. Okay, normal force only have if we're on a flat surface. Now, because the egg falling from the tree is on a planet, most likely Earth, we also have a force of gravity pulling it down. We always have the force of gravity if we are on a planet. Okay, problem 3. A flying squirrel is gliding from a tree to the ground at constant velocity. It says this time we have to consider air resistance. Let's see what that looks like. So gravity is pulling down for sure, and the squirrel is on Earth, so we have our force of gravity. Now, you might think we have an applied force, but because the squirrel is drifting down at constant speed, remember, force has to have acceleration. So because it's moving at constant speed, there is no applied force. Now, this brings up a new force here, air resistance force. Anytime an object is in motion, there's going to be something that slows it down. Okay, if it's moving through the air resistance is going to be the force slowing it down. Now these forces that act to slow things down always act in the opposite direction of motion. So because the squirrel is falling to the ground, moving downward, the air resistance is going to face upward. All right, example problem 4. A rightward force is applied to a book in order to move it across the desk. Consider frictional forces. Ignore air resistance. Let's see what that looks like. Now, on this one, we've got 4 of them. Sounds crazy, but they all make sense. So first off, let's see here. Book across desk. Okay, so the book is on a desk, which is a flat surface. So we definitely have that normal force. Remember, it's if we're on a flat surface. The book is on a planet, so we've got the force of gravity. So if it was just sitting still, we would just have these two, but it's moving. So the book is being pushed to the right. As you can see here, applied to a book, a rightward force. So it's moving to the right, and anytime anything is moving, there's always something there to try and slow it down. If we're moving on a surface, the force that's slowing it down is the friction force. And remember, these forces that slow things down always act in the opposite direction. So because it's moving to the right, the frictional force is going to be moving to the left. All right, problem 5. Skydiver is descending with a constant velocity. Consider air resistance. Okay, so in this one, of course, the skydiver is probably on Earth, so he's being pulled down by gravity. Now, he just fell. I won't say fell. Let's say he was dropped out of the airplane. So he's not accelerating. There's no applied force. There wasn't some slingshot shooting him down. So there's no applied force or anything. Now, because he is moving through the air, there is a force that needs to be present to slow him down, and that's the air resistance force. Now, that's going to face upward because he's moving down. Remember, these forces that slow people down always act in the opposite direction of our motion. So because he's moving down, the air resistance is going to be facing upward. Problem 6. A man drags a sled across loosely packed snow with a rightward acceleration. So, key point here, rightward acceleration. So because he's accelerating to the right, we do have an applied force acting in a rightward direction. Now, let's backtrack a little bit. Because he is on a surface, there is a normal force. Because he's on a planet, there's going to be gravity. Now, it says here he's dragging a sled, so the sled is moving. He's accelerating, which is why we have the applied force. And because he's moving on a surface, we do have a force slowing us down, and that's our frictional force. Now, because we're moving in the right direction, these forces that slow us down always act in the opposite direction. So because he's moving to the right, the friction is going to face the left. Problem 7. Football is moving upwards towards its peak after having been booted or kicked by a punter. So this one, people get confused on. Because it's at this, we've got our motion path. Let me draw one here. It'll be a little bit rough since I'm using a mouse, but the motion path kind of looks like that. That worked out better than I thought. Okay, so since it's at the top of its motion path, football going, it's about right here. The only thing pulling it now is the force of gravity. So if it's talking about like a cannonball, a volleyball, any sort of sports ball, okay, if it's at the top of its motion path, the only thing pulling it to the ground is the force of gravity. And we can say that on this one because it's not a windy day. They should have said that in the problem, but there's no air resistance, so we don't have to worry about that on this one. Now, ideally, since it is moving, there should be one, but we're not on this one. Problem 8. A car runs out of gas and is coasting down a hill. So on this one, notice it says coasting. Coasting means we're moving at a constant speed, so we're not accelerating. That's why there's no applied force on the right. But since we're coasting, we are moving. So since we're moving to the right, There's got to be something to eventually stop us, and so we have to have some sort of force that acts to slow us down, and that is our frictional force. And it's going to be facing the left because these slow down forces always act in the opposite direction of our motion. So because this guy is moving to the right, the force slowing us down is moving to the left. Now, because we're on Earth, there is gravity. Because we're on a hill, a surface of some sort, there's also a normal force facing straight up. Alright, so guys, that's all I got. Thank you for listening. Make sure you got these notes filled out, and have a great weekend.